to the hour. So good afternoon, good morning, late good evening, wherever you are. This is the International Space Science Institute from Bern in Switzerland with the ISI Game Changers online seminars. And I'm Tilman Spohn, and I'm your host again today. So in this series of 10 talks, we're have seminars on habitability from galactic to microbial scales. And we looked at the habitable zone in the last talk. And we we'll see, how, life can change habitability. But today, we'll be talking about whether or not water and rock is all that is needed, or is there more to it to make a planet habitable? And we have an expert on this question with us, one of the world-leading experts on this, Frances Westall, who will brief us on this. She is from the University of Orléans, the director of the research at the Centre de Biophysique Moléculaire Exobiology, and this is in CNRS institution. This laboratory is associated with the University of Orléans. Now, Frances works a lot in South Africa, and this is actually where she's from. She was born there, but she studied in the United Kingdom, and after a time, I think in Germany and in other places of the world, she, for some time ago, settled in Orléans. Well, Frances, we're very glad to have you here with us and hear your presentation on this subject, and the floor is all yours.
Thank you very much, Tilman. Thank you for this invitation and the chance to talk about water and rocks, because I'm a geologist, so I like rocks. I want to show you today basically how the importance of, we'll talk about the importance of geology for the emergence of life, or for habitability, the emergence of life, etc., and the influence of geology on the evolution of life. So I'm going to start off by stating that I'm going to talk about life as we know it, based on carbon and water, and I'll show you why. Then I'll talk a little bit about the geology of the early Earth as the context for the emergence of life. I will then I have a few slides on prebiotic chemistry, and it's my version of prebiotic chemistry. So it's a very simple geologist understanding of how life emerged, and this on the early Earth, the Hadean Earth. Then I will briefly address the co-evolution of Earth and life and look at the implications for other worlds. So life as we know it, based on carbon and water. Why carbon and water? Well, this is an old chart, but it shows the abundance of elements in the universe. And in the orange here, you'll see all the life essential elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. They are all up front. These are all amongst the most abundant elements in the universe. So also the elements for water, plus the carbon and various other elements, as well as transition metals that are very important. But I won't talk about those today. I just wanted to say that they're also important. So given that these are the elements that are most common in the universe, well, it's most likely that life uses the common elements, that these will be the elements of life in the universe. But it may not be the only form of life. And I'm not going to talk today about weird life, other types of life forms. There's some really good books and papers about those, but I'm just going to concentrate on life based on organic molecules and water. So let's jump into the geology of the early Earth and the context for the emergence of life. So the Earth, I've got two images of the Earth here. The one on the left is, of course, the Pacific Ocean viewed from space, and the one on the right is my homeland, South Africa, viewed from space. Now, the difference here is here we see, if you only look at the planet from this point of view, you think here is an ocean world. If you look at the planet from this point of view, you see continents. The ocean world was typical of the early Earth more than 4 billion years ago, or even 3 billion years ago, because there were no continents like there are today. So how did we get from there to here, and what does it mean for life? I'll be going back and forwards through this question throughout the talk, and you'll see why. So this is a sketch that I took from the NASA website, the NAI website, that I like very much, showing the evolution of the Earth from the primordial condensation of the planet about 4.56 billion years ago, the condensation of water on the planet, prebiotic molecules coming together to form first life forms that become more complex, sophisticated, that come until we get the diversity of life and life on land much later on. Now, the consolidated at 4.56 billion years ago, but the oldest well-preserved rocks we have formed only 1 million years afterwards, 3.5 billion years ago. But we do have crystals called zircons that formed in the period between 4.3 to 4.4, 3.9 billion years ago. These kinds of crystals are very robust, so they can be formed, eroded from the rocks, sedimented, made into rocks again, re-eroded, etc. So, and we can date these crystals. So we know that there was crust around probably from about 4.3 billion years ago, and then between this period, between these two periods, there are a few crustal remnants. They're not very many, but they're heavily metamorphosed, and it's very difficult to tease out information about the environment from these rocks. So I'm going to concentrate on what we know from these well-preserved rocks, but they're pretty good analogs for what came before. So in terms of life, well, we have, I'll talk about the prebiotic building bricks of life. When did life emerge? Well, probably as soon as we had liquid water on the surface of the planet, about 4.3 billion years ago. But the oldest traces of life that we have, the well-preserved ones, are in these 3.5 billion year old rocks that are found in South Africa and in Australia. There are tentative indications of life in rocks older, about 3.75 billion years old, from the Isio Greenstone belt in Greenland. But as I mentioned before, these are really heavily metamorphosed rocks. And then big change around 2.4 billion years ago, when the composition of the atmosphere became more enriched in oxygen, which allowed the evolution of more complex organisms, eukaryotes. We don't know when the eukaryotes appeared, but we find some remains about 1.6 billion years old. And there was at 0.6 billion years, like 600 million years ago, 540 million years ago, there was a great diversification of life. We can see this in another way. Here is the geological timescale on the left from the consolidation of the Earth through the Hadean, the Archean. This red area here, the Precambrian, is a very, very long period in Earth's history. But a lot of things were going on there that we can't see. But most of what we can see happened just around here in the last 550 or 60 million years or so. So just keep in mind that David Catlin spoke about atmospheres the last time. The early atmosphere of the Earth was basically carbon dioxide with some other gases such as methane and so on. And oxygen, the atmosphere of oxygen that we know today, only started rising significantly about 2.4 billion years ago, the great oxidation event, and look at what happens with the life. So this is when we think that life probably emerged during the Hadean, and the early life forms would have been extremely primitive microbes, something similar to these. This is a scanning electron microscope image of a chemolithotrophic microbe. And then they evolved into photosynthesizers. And the photosynthesizers, again, we're still in a carbon dioxide world, but the photosynthesizers later developed into or mutated into organisms, or through symbiosis were able to break down, well, they obtained their energy from sunlight. They were able to break down the water molecule in order to obtain energy. And so doing, they released oxygen. And this is how oxygen started appearing in the atmosphere for here. And through much of the Precambrian, of this period of the Precambrian, we're looking at basically an algal world. These are stromatolites, typical of the photosynthetic cyanobacteria. We're looking at basically a stromatolitic world. And then, because of the increase in oxygen and the complex appearance of microbial complexity or organic life complexity, these more complex organisms. This is the period between, there's I think David Catling last week spoke about the boring billion. This is the boring billion period when nothing much happens. We just have these plus the microbes, the smaller microbes. But then after this, some further increase in oxygen in the atmosphere, we get this amazing diversification of life. Excuse me, I put Nelson Mandela there because I think he's one of the foremost statesmen of the last century. Problem is, we've lost the first part of his history. So why did we lose it? Well, it's all related to the history of the Earth. After consolidation, the Earth was still very, very hot. There's a lot of recycling of the ancient crust through various forms of tectonics, plume tectonics, later plate tectonics, also through impacts. The crust was really remobilized. Some of it was incorporated in at least the G chemical signature was incorporated in the later crust. But the early Earth was hot. We go from the consolidation of the Earth from planetesimals about 4.56 billion years ago. The Earth started to solidify. There was early degassing, and then came an impact with a body the size of Mars, Theia, which had created this moon-forming impact, and everything basically started all over again. But continued impacts. The flux of impactors, asteroids, and meteorites continued with various effects on the surface of the Earth. So the Earth, again, I repeat, the Earth was really very hot, and we can imagine the early continents forming as extrusions on top of a plume. Sorry, I'll go back again. If you see the mantle plumes coming up from the Earth's core, they exit at the surface, and so doing, they produce volcanic extrusions. And this is a cutout of Iceland, which forms on top of a mantle plume. So this is how the early continents formed. We have, and they formed small exposures, oceanic plateau on top of these hotspots, just to reinforce the idea of heat. And I'm also going to reinforce here the idea of hydrothermal activity. Think about Yellowstone caldera forming above a hotspot with much, we all know about the hydrothermal activity going on there. So this was the early Earth. Now, because of this very high heat flow, the early crust, well, the hypothesis of the early crust was thicker than it is today, just because of high heat flow, or maybe not. But in any case, it was quite weak because it was thick, it was hot, warmer. So if you look at this sketch here of plume coming up to the surface of the Earth in the water, you can see all of these faults around the plume. These are cracks, and because of the weakness in the crust, the upper crust, there's subsidence which forms basin-like structures, and this is shown in a box model here from a paper by Wout Nijman, who's a fantastic structural geologist, sedimentologist from the University of Utrecht. And what you see here is the green and the orangey colors. These are the land masses. The orangey colors are the volcanic edifices. But you see sort of circular basin-like structures formed related to this faulting. And these are similar. These are shallow basins on the top of oceanic plateau. And we can see the remnants of these in the rock, the well-preserved rocks at 3.5 billion years ago. And this are probably similar to coronae structure that form on the surface of Mars and on Venus. I'm going to zoom in on the edge of one of these basins here. And this is my own very simple box model sketch to show what the environment of the early Earth would have looked like. So we have our volcanic edifice here, exposed land masses. This is the water body. Here we have a volcanic layers and layers and layers, thick layers of volcanic lava overlain by volcanic sediments. But note, there's a huge amount of hydrothermal activities going on here, with hydrothermal vents popping up all over the place. And these sort of cauliflower structures are supposed to be hydrothermal vents that we don't see in this front section. And again, and I'll talk about this a little bit later, a lot of impacts of extraterrestrial material and carbon dioxide atmosphere. So now we're going to come on to the part on prebiotic chemistry and the emergence of life on the what do we need for life? What are the ingredients of life? Well, we need organic molecules, prebiotic molecules. We need water. The prebiotic molecules would have been formed on the Earth by endogenous processes, and they were also imported by extraterrestrial materials. We need energy. And for energy, we have UV radiation, photons, heat, redox chemical reactions, and also we need the geological context. So let's have a look at the organic molecules. Formed on the Earth in the very early pre-moon forming impact in reducing atmosphere, there would have been organic molecules, but they would have been destroyed during the moon forming impact. But there was a lot of, there are processes going on in the crust serpentinization processes, using Fischer-Tropsch chemistry that alters the rocks and produce, in so doing, in the presence of water and containing carbon dioxide. We also, you can get the production of organic molecules, small, but these are small molecules. And then there's a huge amount of, there's a huge influx of extraterrestrial organic molecules in meteorites, such as the carbonaceous chondrites, and also in some micrometeorites. So the endogenous source is permanent. We're still finding this, the molecules coming out of the vents today, but it's a minor source. The extraterrestrial origin from space is a major source. Carbonaceous chondrites are about 4% of all meteorites that hit the Earth, and they contain up to 4% organic matter. The micrometeorites, there are certain micrometeorites that can contain, the ultra carbonaceous ones that can contain up to 80% organic matter. So, and these meteorites contain a huge range of different kinds of organic molecules, from amino acids, purines, pyrimidines. Schmidt-Coplin and his colleagues found about 14,000 molecular compounds in the Murchison meteorite and 70 amino acids. And these are some other types, some of the classes of compounds found and their concentrations. So there's a huge amount of material coming into the Earth. Most of it is refractory organic matter, 75%. About 25% of these molecules are volatile, so they readily dissolve in seawater. And this material, this organic material, that extraterrestrial material, will have formed in the outer reaches of the solar system, the inner reaches being far too hot for the formation of preservation of these organic molecules. So the delivery of the volcanics of volatiles and carbonaceous material to the Earth would have started already during the consolidation of the planetesimals, also during the giant impacts such as the one that formed the moon, and also through the late Vernier and continued meteorite impact. So this again, coming back to my little sketch to emphasize the importance of the importation of this extraterrestrial carbonaceous material onto Earth. So we have evidence of impacts on Earth in the meteorite craters. For instance, impact craters, for instance, meteorite crater in Arizona, and the Frida Fort Dome in South Africa is 2 billion years old. I think recently an older crater was found in Australia, but this was 2 billion years old. So we have evidence for impacts also in the early Earth sediments, the well-preserved sediments. There are a number of layers of spherulites, impact spherulites that look like these, and they're associated with nickel and iridium, typical impact signatures. And these spherulites are actually very pretty, aesthetic. One of the things I like about geology is that rocks are pretty, or can be. So these spherulites, this is what they look like. But all of this evidence, it's either physical, structural, or rocky. But where's the organic matter? We don't find organic matter in these until recently. And this is a paper that we published with Didier Goury, my colleague from Paris, in which we describe how we found extraterrestrial organic matter associated with some of the oldest sediments. And these are sediments from the Barberton Greenstone Belt in South Africa. This is the first evidence for extraterrestrial carbon in terrestrial sediments, not even the KT impact feature. There's no carbon associated with that. So what did we find? Well, this is an image of a rock from Barberton. And what we are looking at are layers and layers of volcanic ash sediments. The gray layers are thick layers of volcanic ash. The darker layers are enrichments of organic matter. And this sketch here above shows a basin, sedimentary basin with the sediments accumulating and hydrothermal fluids sourcing in the sediments and flowing back into the sediments. We'll come back to this. Now, my colleague Didier Goury, he was in my office when about, don't know, 2011, about 2010, 2011, and he saw this fragment of this rock on my desk, and he said to me, can I take it? I want to use my EPR spectroscopy method, which is electron paramagnetic resonance method. I want to analyze the organic matter to see, because he uses this method to determine whether the organic matter in a rock is, let's say, of great age, Archean age, or if it's younger. There are various physical parameters that this method measures, which are related to the structure of the organic molecules. And they can be used to distinguish the age of the rock, or help to distinguish the age of the rock. Well, he phoned me up about a year or so later, and he said, "Francis, there's something really weird about this rock. I need to come and speak to you." So he showed us that this is the spectrum of this rock. He cut this rock into about 40 slices parallel to the bedding. And in this particular slice here, he found a peak, this peak here, which is, I'll show you, but it's related to the extraterrestrial carbon. And it was associated with other peaks related to nickel-rich spinels, which are identified as cosmic nanospinels. Well, this is a typical spectrum of the electroparamagnetic resonance. And if you measure different parameters, such as the line shape, line width, and peak height, you can use these parameters to classify the organic matter in the rocks you're looking at. So in this rock, the other dark layers are classed into this sector here, which is typical for organic material from the Archean. But Didier, he's analyzed hundreds and hundreds of rocks and meteorites, etc. And this particular layer fell into the carbonate, that of the carbonaceous chondrites, which is why he said to me, "This is weird." So it turns out that this particular layer is enriched in carbonaceous matter of extraterrestrial origin, probably rain of micrometeorites that just happened to land when there wasn't volcanic eruption, and it wasn't diluted by volcanic ash. But this layer, it's 1 millimeter thick, but it's very extensive. We've been able to map it for over 2 kilometers and probably even further. So anyway, so this is an interesting anecdote. Let's set the scene for the origin of life. The early Earth, we have our early Earth, which is an ocean planet that actually had extreme environmental conditions. It was anaerobic, carbon dioxide atmosphere, there was no ozone layer, it was basically hot. These shallow basins on top of hot spots with hydrothermal vents coming up that heated up the water. Estimations for water temperature are quite varied, but most people concur these days that at least the temperature of the water close to the rock-water interface was about 60, 70 degrees centigrade. So it's a wee bit hot for us. Seawater would have been acidic because of the carbon dioxide atmosphere. Salt contents seem to have been higher, and the seawater composition was richer in transition elements than today. So the environmental conditions were very extreme, but there was also on various scales, micro to macro scales, incredible variability in terms of physicochemical parameters, and this is important for the emergence of life. So this is my one slide showing you how life emerged from my point of view. You have your ingredients and water, and you need plus the energy of the various forms of energy. You need some kind of catalyzer to stimulate the chemical reactions. You end up with a living species, which apparently, according to my prebiotic chemist colleagues, may simply be a pore in a rock with some kind of information transferring molecule and other useful molecules. And then you end up with a protocell, which has RNA, proteins, membranes, something similar to this. Now, for all of this, you need minerals. Where do the ingredients come from? They come from minerals. They're volatiles imported in the planetesimals, in the meteorites, etc. And what kinds of minerals? Well, the early Earth was enriched in highly reactive minerals, such as olivine, pyroxene, potassium feldspar, clay, zeolites, and sulfides. And they all occur in the kinds of rocks that were very common on the early Earth. These are rocks enriched in magnesium and iron, mafic, ultramafic rocks, also found in meteorites and also formed, useful in serpentinization reactions. Now, the minerals are important because they help concentrate organics. The minerals have particular crystal lattices, which can help the structural organization of the molecules that are fixed to their surfaces. They can be altered, and the chemical alteration can produce energy in small organics, as in serpentinization reactions. And because they have specific orientations in the crystal lattices, for instance, quartz, this can affect the what we call the chirality, the handedness of the molecules. So that minerals are very important. But so we can say here, no minerals, no life. So this is the answer to your question, Tillman. Yes, rocks are very important. No minerals, no life. And probably no rocks and hot water, no life, because we think that hot water hydrothermal reactions were very important. So this is a sketch of what the early Earth may have looked like, with some spots of emergent land masses. Life probably, the prebiotic processes that led to life would probably have started basically as soon as there was stable liquid water at the surface of the Earth. For those working in prebiotic chemistry, we think that there's a natural evolution from chemistry to biology, totally natural process that will take place anywhere where you have the right conditions and the right ingredients. But where did life emerge? There are all kinds of hypotheses: hydrothermal environments, pumice rafts, the beach splash pools, subaerial springs, or even deep faults. We'll have a look at some of these. So the most popular idea for the emergence of life is the emergence of life associated with hydrothermal environments. Here I've put in an image of a black smoker, but it could also have been a white smoker, a low temperature vent. And in this image, this is from the seafloor close to Milos. I think it's the island of Milos on Greece, where it looks sort of fuzzy, but that's because there's hydrothermal fluids just seeping up through the water. And this is really important from our point of view, and I'll show you in a few minutes why. Martin Brazier and his colleagues looked at the possibility of pumice rafts being useful for the important for the emergence of life. This is an image, an artist's view of the early Earth, showing a lot of hydrothermal activity on the surface. So we'll have a look at that. We'll start with the scenarios related to the emergence of life on emergent land surfaces. So the here are taken from a paper by David Diemer and David Damer in Astrobiology in 2020. They imagine life emerging in some kind of hydrothermal pool on land. And because it's on land, we're in a basically hot environment. You're having wetting, drying cycles, which is apparently important for complexification and concentration of the organic molecules. So the life will start in one pond, and then it may, through these cyclic wetting, drying processes, the first cells can emerge and then would be taken through rivers, streams, ponds, and end up in the sea. And here that we have some stromatolites already, very advanced. So I have a big problem with this scenario, but there are a lot of people who really think that it's important. And my problem is related to UV radiation. There was no ozone layer on the early Earth. So the flux of UV radiation was a lot higher than it is on the Earth today. There was UVC radiation and high doses of UVB radiation. Charlie Cockell and his colleagues calculated that radiation doses were between 5 and 1,000 times higher per meter squared DNA weighted compared to today. And this is huge. So, but on the other hand, UV radiation is also useful for certain prebiotic processes, because when you're trying to get the molecules to stick together, and in prebiotic chemistry, you've got to get the necessary molecules together, and they need to stay together. They mustn't be broken apart. They mustn't have a chance to go backwards. It has to be a forwards process. They need to stick together, and like a snowball rolling down a slope, and gradually get more and more and more complex. And to do that, you need some kind of high energy to get over this activation point. This is from a paper by Robert Pascal and his colleagues in 2013. So to a certain extent, UV radiation is a good source of energy for early prebiotic chemistry. This is taken from a paper by Böttcher in 2018, showing gradual complexification of organic molecules, starting with very simple molecules on the left and very complex molecules on the right. Now, UV radiation helps the nail formation of smaller molecules down here. But as soon as the molecules get above a certain size and a certain size of interest for life, it's bad, it breaks them up. So that's why I have a problem with UV radiation and the emergence of life on land. So what does this mean for the emergence of life elsewhere? If we're basically looking at landlocked wells with lakes or just emergent surfaces. We can think about Mars, exoplanets, maybe Venus, but we don't know what happened there. But if this were the case, then life could not have emerged on ocean wells. So let's have a look at hydrothermal environments. We have the hydrothermal vents. And in fact, John Barros and Sarah, I think her name was Sarah Hoffman in 1985. They were the first to suggest that life might have emerged in hydrothermal vents. Why hydrothermal vents interesting is because there are organic molecules there. There's a lot of energy. There are a lot of gradients, a lot of reactions taking place on the surfaces of reactive molecules. And Mike Russell and his colleagues have been working for very many years, about 25 years now, on this hydrothermal vent scenario. And this sketch from one of his papers, their papers, shows the molecules gradually coursing through the hydrothermal vent, becoming more and more complex until you get some cells emerging. Now, in our group, we suggested that perhaps another scenario would be sediments associated with hydrothermal vents. Reason being that they're very common, and this publication came out in Astrobiology in 2018. And the sediments are highly enriched, also in reactive minerals. The temperature gradient is maybe lower. There are a lot of elements, transition elements associated, and so and then these sediments will also contain some of the extraterrestrial carbon raining down on the Earth. And hydrothermal fluids circulating through one of these sedimentary basins, just circulating, can have a great effect on what's going on in the sediments. So look at one of the sedimentary environment, the sediments here. These are the various sedimentary particles. These are reactive sedimentary particles. There are organic molecules in the sediments. There's a lot of recycling, complexification of the organic molecules, gradients of temperature, pH, ionic concentrations. We've seen that the minerals are, the surfaces are useful for confining, for concentrating the molecules, for helping them to form, get into a particular structure, complexify. These are ideal conditions for prebiotic chemistry. It's just one of the scenarios. But let's look at these in terms of regional compare regional local scales to the micro scales. On a regional scale, we're looking at bodies of water, oceans, lagoons, lakes, deep or shallow. We're looking at exposed landmass with lacustrine environments, maybe hot springs, hydrothermal vents, subaqueous, subaerial, strong hydrothermal influence. And on the micro scale, we have the volcanic particle surfaces, variable temperatures, variable pH, variable ionic concentrations. So we're looking both at the larger scale and the micro scale. So in terms of hydrothermal environments, what does this mean for the emergence of life elsewhere? Well, of course, because there would have been a lot of hydrothermal activity associated with the larger impact, well, with the impact craters on Mars or elsewhere on exoplanets, maybe Venus. This is a paper by Gordon-Zinski and colleagues comparing hydrothermal activity on Mars and on Earth. So this is where the hydrothermal activity would be concentrated on the edges of the impact craters. So either Mars, exoplanets, probably Venus as well. And also subsea on the subsea crust on the ocean planets, early Earth, early Venus, icy satellites, and the exoplanets. So coming up, just got a few aspects that I want to talk about before ending my talk here. So just talk about the co-evolution of Earth and life. This is geology, geophysics. So here at the during the Hadean, in the early part of the evolution of Earth, the hypothesis is that the crust the Earth was just formed of a single crust, what we call a stagnant lid, and that there was some kind of but there were convection cells in this stagnant lid. And plate tectonics that we know that's prevalent today started perhaps to come in during the early Archean period, later on in the evolution of the Earth. We have here an image showing plume tectonics. Sorry, I should have put the origin of this, I've forgotten. Plume tectonics coming up. We can see these splotches here. These would be the as I showed for Iceland, the land masses on top of the plumes, and perhaps some kind of slushy plate tectonics just starting. But then later on, modern style plate tectonics appeared, evolved, became prevalent. But we only have evidence of this kind of plate tectonics starting about 3.2 billion years ago. There's a hypothesis by Stern in a paper, I think it's Robert Stern, in a paper in 2018 in the Royal Society of Philosophical Transactions, in which he hypothesized that increased plate tectonic activity about at the frontier between the Precambrian and the Cambrian, about 560 million years ago. This might have contributed to the changes that may be related to the diversification of life that we see today. So in this period where we have stagnant lid tectonics, this is when life emerged. So on any planet where we have the right ingredients, liquid water, sources of energy, even if it's stagnant lid, life can emerge. However, the first well-preserved crustal rocks at 3.5 million years old, they came in this kind of scenario. The great oxidation event, when oxygen increased in the atmosphere, came when we already had some kind of form of modern plate tectonic system. The emergence of the eukaryotes, modern plate tectonics, diversification of life, modern plate tectonics. So yes, I just wanted to emphasize this evolution related to the geological evolution of the Earth. So I'm going to finish here with a few words about implications about the search for life on other worlds. We're looking at the scenarios for the emergence of life on Earth. These are the scenarios I spoke about on land, undersea, well, I didn't really speak about pumice rafts or deep faults. But these various scenarios have implications for the emergence of life elsewhere. We need to think in terms of scale, because well, life probably, we don't know how long it took for life to emerge from prebiotic molecules to a protocell. We think that this had to have happened very, very quickly, because otherwise, it had to be a snowball effect, because otherwise, if the process stopped and went backwards, you wouldn't get life. So it had to be quick. And we have no idea what the time scale is, because we haven't been able to do it in the laboratory yet. So maybe we're looking at scales of some hundreds of thousands of years, maybe less, maybe up to 1 million years. We don't know. But on that, if we're looking for a body of water in which we have hydrothermal activity on these timescales, we need to be looking at bodies of water of several hundreds of kilometers in diameter. So there we're looking at big impacts, or ocean worlds. So we have our body of water that is big enough, has the necessary ingredients of life, but it doesn't necessarily have to cover the whole planet. And this means that the habitability of a planet can be patchy. You can have different types of habitable conditions occurring at different times and in different places. This is what we call punctuated habitability. So let's look at Mars is a good example of what might potential punctuated habitability. Early in the history of the planet, there were water bodies, and we believe the possibility of life emerging. So we have life emerging at the surface, but then the habitable conditions decreased. The volatiles escaped from the surface of Mars or frozen into the cryosphere. There was some kind of seesawing between, due to the strong obliquity of Mars, seesawing between potentially habitable area and non-habitable area. And finally, with dead microbes at the surface, if there was life in the particular area, perhaps living microbes underground. And if there's a huge impact that hits the cryosphere and there are viable cells there, these viable cells could reach the surface for a certain period of time. So what does this mean about the types of organisms that we might expect? Looking at Mars, 4 billion years ago, there would certainly have been prebiotic processes going on. Maybe some form of life similar to terrestrial chemotrophs would have been there, would have evolved because of very punctuated habitability and the lack of continuous habitability on Mars. Could phototrophs have emerged on the surface or not? We don't know. But today, if we're looking for active extant life on the planet in the subsurface, we'd be looking for chemotrophs or something similar to chemotrophs. And the same would go for the isosatellites at the edge of our solar system. But for exoplanets, well, your imagination, take it where you want, from prebiotic to very simple life forms such as chemotrophs, phototrophs, or more. So this is my last slide. And I've taken you on a tour through the geology, habitability, and evolution of life on the Earth. We're looking at life as we know it because these elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, are the most common elements in the universe. The early Earth was a totally different planet. It had a different geological regime, crustal regime, tectonics, different physico-chemical environment completely. But it's the Earth that life emerged upon. If something happened, something catastrophic happened and all life was extinguished on the Earth today, that would be difficult because there are microbes in the crust. But anyway, let's imagine all life is extinguished today. It would not be possible for life to emerge, at least immediately, because of the oxygen in the environment. It would need for oxygen to disappear for that. In terms of prebiotic chemistry and the emergence of life on the earlier, probably hydrothermal activity associated with minerals, rocks on land or in the sea. Co-evolution of the Earth and life. Well, it's the geological evolution of the Earth accompanied the evolution of life. The geology produced the environment that life for the flourishing of life, but at the same time, it's because of the evolution of oxygenic photosynthesizers, producing oxygen in the atmosphere and having this kind of sort of buffer that helps to keep the temperature at the surface of the Earth quite clement for life. There's a continuous interaction between life processes and geological evolution. But this is why we are here. And all of this has implications for other worlds, whether they're water worlds or landlocked worlds. And I will finish there. Thank you very much.
Thank you very, very much, Frances, for this very inspiring talk. At least I found it very inspiring. And you answered the question. There's
I promised you a lot of geology, tectonics.
But it's complicated. It's complex.
It is.
Thank you very much. So to the audience, you have two ways of asking questions. As you know, those who've been with us previously know about that. You can either write your question in the chat and I will read it to Frances, or you use the raise your hand feature on Zoom and you can raise your hand and then we'll switch between the two. We have already a discussion going on in the chat and let's see how we get Frances involved in that. So it starts out with a question by Mirs Oppenheim. Is it really necessary that organic compounds arrive from extraterrestrial sources? Or just abbreviating a little bit, could it be formed on Earth?
Well, yes, in fact, I did say that there were endogenic sources and these are reactions in the crust, serpentinization reactions that do produce small organic molecules. So yes, there's definitely a source of organic molecules in the crust and possibly even, I think, also in the atmosphere during eruptions. Some processes going on in the early carbon dioxide atmosphere where you have lightning associated with eruptions that could produce a rain of organic molecules. But in terms of quantity, the flux was minor from these sources.
Okay, then Jean-Pierre de Vera asks, why not just have life emerge on volcanic islands? And he goes on about it. And later he asks, why you're insisting on having it emerge in seawater while life consists of fresh water in the molecules.
Yes. Hello, Jean-Pierre. I'm not too sure. Well, I don't know if you wrote that that comment before or after I spoke about the the problem with the UV radiation. I mentioned that UV radiation it provides an important source of energy for activation energy in the early part of prebiotic chemistry processes, but in the later part, it breaks up the molecules. So it's quite possible that, for instance, to be honest, personally, I think that maybe the emergence of life is a mixed, the organic molecules that came to form life may have probably had origins from all over, not just subaqueous hydrothermal environments, but also coming in by rivers from, smaller molecules coming in by rivers formed by, in a UV-bathed environment, a hydrothermal spring on land. So I personally think that life emerged underwater just because of these problems. But I see no problem, and also in terms of timescale, because the subaerial environments were quite unstable. Anyway, so yes, it's debatable, but I think UV radiation on the surface is important to a certain extent, but afterwards it's destructive.
Okay, let's have one more from the chat, and then we go over to the raised hands where Jean-Pierre has raised his hand already. So there's one interesting question, one more interesting question. You make a clear case for the requirements of minerals and their contact with water. Does this fact argue against the emergence of life on Europa and other ice-covered moons in the solar system? So what if you had no minerals but ice?
No, not at all, because these icy worlds, it's the exterior that's icy. If you go if you look at the structure of these worlds, there's a core, there's a mantle, there is rock in contact with seawater below the icy crust, and probably, at least with Europa, we think that there's probably some kind of, or there may be some kind of hydrothermal activity due to tidal forcing with Jupiter, and maybe the same with the other icy satellites. So no, it's not a problem if there is no emergent landmass. And I think I hope I made it, well, maybe I wasn't clear enough in my talk, but I did say that in hydrothermal environments, we think they will be found on these icy satellites.
Okay, let's go over to the raised hands. The first was Sanjay Limai, and Willie, can you open the mic for Sanjay? Sanjay, I think you should be able to speak once you unmute your microphone. We can't hear you, Sanjay. So Willie, have you allowed Sanjay to speak?
Yes, but he has to unmute the microphone by himself.
Oh, now he did. Okay.
Can you hear me now?
Yeah, we can hear you now.
Oh, very good. Thanks.
Oh, you have a feedback.
No, sorry, what happened was I couldn't hear the talk on my laptop, so I had to open it on the iPhone. So there's an echo, but it's far enough away. Anyway, my quick question was, do you have any thoughts on when the molecular clock may have risen?
Oh boy. I think the people working on this, on molecular genetics, etc., they're doing fantastic work. I think it's not easy. This is way out of my field, and I think it's important to correlate the molecular clock with what we do know from the rock record. And that, that way, you can say, okay, we have the molecular clock suggests that oxygenic photosynthesis arose at this particular time. Do we see evidence in the rock record for the emergence of oxygenic photosynthesis? We think oxygenic photosynthesis arose about 3 billion years ago through mutations, through symbiotic reactions and so on. But we've got no evidence because everything, the whole Earth was totally reduced. It would take a long time for the oxygen being pumped out. In the first place, the oxygen would be a poison for the microbes. And then it would take a long time for the surface of the Earth to, all of these reducing components to be oxidized, and then for oxygen to arise in the atmosphere. So it's a very difficult task, and I take my hat off to the people who are trying to do it. It's an iterative task.
Okay, Jean-Pierre, you would be next.
Jean-Pierre, you weren't happy with my reply?
So do you hear me?
Yes.
Yeah,
Okay, that's working. Thank you. Thank you for you have always brilliant talks, and I enjoy it because it's also really on the point. You are really pointing out what is essential, and on this what you just responded. I have still some difficulties because of this freshwater story in the cells of life. Always you have fresh water, and for me it's more an indication that volcanic islands should be the area where life the first time emerged, because not just you say about UV radiation, but you mentioned also that UV radiation is also forming other kind of organics, not just destroying. And think about volcanic islands, the rocks, and you have a porous rocks also there, where fresh water is penetrating. And this is a kind of stability, but in the deep sea, you have much more salty water. And this is something that I'm often struggling about.
Yes.
And
okay, in actual fact, Jean-Pierre, I took out a couple of slides related to this because we have geochemical evidence for the arrival of fresh water through rivers in the coastal areas. And the hydrothermal sedimentary hypothesis for the emergence of life that I spoke about from my group. This would be influenced also by river inputs. So I don't think it's an either or question, but and it may simply be because I'm not a biologist, I'm not a prebiotic chemist, I'm just a simple geologist. I really do have problems with UV radiation for complex molecules.
This, I agree.
The formation of the smaller molecules, apparently it's important, but for complex molecules, it's a problem for me.
Yes, I agree with you, but you think about this kind of microcavities, and there these first formation of cells are protected against UV radiation, and this is something where they are in contact with the atmosphere. They're in contact. I think that life, because it is often you find it at phase gradients, between liquid and gaseous areas.
Okay, that's I see what you're getting at, Jean-Pierre, and you may be, that may be a possibility. The problem is then the organisms have to get from these protected cavities across the land surface through to the sea without being zapped.
Rivers, flowing water coming through.
Can I ask?
Sorry, we have to discuss later.
Yeah, I guess if we were in a conference, I would ask you just to speak offline, but I think your communication,
Okay.
Jean-Pierre, we need to discuss this.
Absolutely.
Great. This is a question by John Rummel. This may be a bit off the thrust of your presentation, but I'm interested in your opinion. Aside from general energetic arguments associated with an anaerobic environment, can you point to any specific reactions, characteristics associated with multicellular life that cannot take place in an environment that doesn't contain loads of free oxygen?
John, hello. Thank you for the comments. I don't think I'm the right person to answer that. Maybe Jean-Pierre could answer it. I've been so concentrating on the really primitive life forms that I haven't really considered sort of the more evolved life forms, the multicellular life. In my primitive understanding, multicellular life, eukaryotes need a lot of energy, and the best way to obtain this energy through oxygen, using oxidizing or reducing components. So it seems to me that multicellular life really does need oxygen. I'm not too sure if this answers your question, but as I said, I'm not an expert for this.
Okay, let's go on with another question here that is possibly simpler to answer. Where does the constraint on the decisive body of water for the emergence of life come from? The mentioned n times 100 kilometers.
Okay, it's discussions with other colleagues. We need a body of water that can last for hundreds of thousands of years, up to 1 million years, in which there is active hydrothermalism going on. So a small body of water won't work, because if it's a small impact crater, the hydrothermal activity will die down very rapidly. So you need, this is why the size, it's not particularly constrained. We just need a body of water that will last, that will survive for sufficient time for life to emerge, with a body of water with hydrothermal activity.
Okay, that's another interesting question. It took billions of years for advanced forms of life to form. Why do you expect that life formed so quickly after Earth formed? And second, why do you expect that the first stage was comparatively so short? And the question is by TSVI.
Okay, so sorry, what was the first part of the question?
Why do you expect that life formed so quickly after Earth?
Oh, yes. Okay. Okay. This is because we think that the emergence of life is a natural consequence of chemistry in certain environments. You have a certain environment, such as the environment of the earlier. You have your organic ingredients, you have water, the various sources of energy, and there will be prebiotic reactions will take place naturally, automatically. And so from this point of view, well, if probably as soon as water was stable on the surface of the planet, I think one of the questions was asking about that. How do we know that there's water 4.3 billion years ago? We don't really know. I think we're using geochemical signatures that are inherited from crust formed at that period that can give us some more information. It's very complicated. It's beyond my understanding. But anyway, and also based on models, the Earth will have cooled down early enough, perhaps even by 4.4 billion years, cooled down sufficiently for water to have condensed on the surface. Processes can start right away. And I personally think that, well, the prebiotic processes will have started wherever, in whatever environment that was suitable. And maybe life emerged more, in different places at different times. Maybe it emerged and then was destroyed for one reason or another, like an impact or so, or re-emerged. Sorry, the second part of the question was?
Where is it? Why do you expect that the first stage was comparatively so short? It's more or less the...
Yes, that's what I answered.
Yeah. Okay. The underway, and I think I can combine An's question with the one from Twain Lawrence. So An was asking, do you think that chemistry would allow life on Titan? And then Twain asks, how optimistic are you about finding life on Europa and other icy ocean worlds in the outer solar system? So Titan and the others.
Titan and the others. Yes, Titan is an interesting case because soon after the planet formed, there may have been the possibility of at least prebiotic chemistry and possibly even early cells. But today, it's believed that there's a layer of liquid water, but it's between two icy layers. There's no energy getting in there. There are no rock particles, microbes like rocks. I call the chemolithotrophes the rock eaters. So I think today there's not much chance of life on Titan, but I wouldn't preclude the possibility of at least prebiotic chemistry, maybe some protocells during the very early evolutionary phases of Titan before it just completely froze over.
Okay, Yang Wang asks, what's the evidence for that water was stable at 4.3 billion years ago? And what did you mean exactly by stable? Is it that the rate of degassing of water from the interior became stable, or the delivery of water from external sources became essentially
okay?
Yes,
Basically, modeling shows that water could have condensed on the surface of the planet. By stable, I mean that you don't have a steam atmosphere, you have liquid water at temperatures below 100 degrees centigrade. And stable meaning in depressions for long enough time for prebiotic processes.
Okay, the next question just continues on that. I mean, would a hot, steep, early Earth, temperatures between 1600 degrees centigrade, support the emergence of life? The oceans might be boiling near the equator and condensed.
No. Just as we don't like water that's too hot, even for prebiotic chemistry, water that's too hot is too hot. Once temperatures get above about 150 degrees, or somewhere between 130 and 150 degrees, the organic molecules that are trying to stick together, because you've got to get the organic molecules together, they just break apart. So no, life couldn't possibly emerge in a steam atmosphere.
Okay, John Gumbley asked, if many biochemical reactions, I guess that means, are condensations, that means amino acids to make proteins, how likely are they to occur in aqueous environments, and how?
Well, that's a question for a prebiotic chemist. Apparently, these reactions occur very easily. I mean, if you look at the carbonaceous chondrites, the carbonaceous meteorites, there's a huge range of molecules, the organic molecules that are formed that formed on the original asteroidal bodies from which the meteorites came. But yes, there are a lot of laboratory experiments trying to put molecules together so that they form bigger molecules, proteins, etc. And it's not easy. Most of the prebiotic chemists have been, well, until recently, they've been concentrating on typical chemistry, which is putting molecule A together with molecule B to get molecule C. That's a controlled reaction, but on early Earth or anywhere else, there was no control. You know, it was molecule A to Z all together, mixing up, and you know, you get X number of variations. So it's, yes, it's work that is ongoing. It's painstaking work, but these days there's more groups that are trying to do prebiotic chemistry in more realistic geological environments.
Okay, this question exhausts the questions in the chat, and I can only agree with Andrea Kotlova, who writes, "Thank you very much for this amazing talk." Applause and a big smile. Thank you very much, Francis. This was a great talk. And thank you very much for listening in. Next week, we have Aditya Chopra talk to us about life as an agent for sustaining habitability. So the interaction between, or the co-evolution of life and the Earth, basically, you know, or another planet that Francis alluded to, and, you know, how would the two interact and stabilize habitability. So looking forward to this talk and looking forward for you to come back. And thank you very much. Have a good day and a good evening. Bye-bye.
Thank you very much.